Alright, welcome to one more security tips video. And today I want to talk about the importance of elliptic curve cryptography when it comes to TLS and how to configure web servers to use an elliptic curve that is recommended by the NSA to protect top secret information. First, let's understand the importance of elliptic curve cryptography when it comes to TLS. But for us to have a better understanding, let's have a quick overview of some of the key exchange mechanisms that we can use with TLS. Last week I posted a video about cipher suites, and if you haven't watched that video and you don't know what a cipher suite is, I would definitely recommend that you watch that video before watching this one. But if you remember, one of the things that a cipher suite defines is the key exchange mechanism. There are two popular key exchange mechanisms, RSA and Diffie-Hellman. Let's start with RSA. So if we use RSA, this is what's going to happen. After the client initiates a connection to the server is going to send an SSL certificate back to the client that contains the server's public key. After receiving the SSL certificate from the server, the client is going to extract the public key from the certificate, and it's going to use that public key to encrypt a secret. And here you see that I'm not going to go into too much details about this communication. I'm going to try to simplify as much as I can, just so you can understand the overall process. When the encryption is done, the client sends back to the server the encrypted secret. And what the server does is it takes its private key, which is installed on disk in the server, and uses that to decrypt the secret that it was sent by the client. At the end of the process, the client and the server agrees on the same symmetric key or session key. I'm going to call it session key from now on. And then they use the session key to encrypt the traffic. Now, if you ask me the question, is the RSA key exchange mechanism insecure? I would say the RSA itself, it's not. If an attacker gets the public key from the server, which is in the certificate and it's public anyway, so they would be able to do that very easily, they would not be able to figure out the private key just by taking a look at the public key. So that's not an issue. The issue here is this. Imagine the following situation. We have an attacker that is recording data transmission between a client and a server, and what they do is that they're going to keep this recording. Then a year later, the server gets compromised and the attacker is able to obtain the private key. If that happens, the attacker can very easily use the private key to decrypt the session key. And then from there, with the session key, they would be able to go back in time, a year back, and decrypt all of the data that was sent from the client to the server. So the problem here really is that the private key, which is a long-term secret that stays in the server, is being used to protect the session key. Now let's take a look at another and very popular key exchange mechanism, Diffie-Hellman. In this picture here, let's say that Alice is the client, Bob is the server, and Charlie is the attacker. After Alice starts the communication with Bob, what Bob's gonna do is, Bob has a prime number P and a generator G, and then it's gonna generate a private key, which is another number, and here we're calling lowercase b. Then what Bob's gonna do is, it's gonna calculate G to the power of B mod P, and that's gonna generate uppercase B. And here, lowercase b is our private key because that's never gonna leave the server. Now, the public key is uppercase B because that's what's gonna be sent back to Alice. So Alice is gonna get P, G, and uppercase B. Then Alice is gonna calculate G to the power of A mod P, and that's gonna generate the public key, which in this case is the uppercase A. Then the next step is for Alice to send the public key all the way to Bob. And then what they're gonna do is to do some calculations to get to the same shared secret S. This is just another approach to key exchange, but the problem is still the same. The private key that was generated by Bob, it's probably gonna be used for different sessions. And if Bob was compromised and the attacker Charlie was able to obtain lowercase b, Charlie would be able to decrypt the traffic between Alice and Bob and either other clients and Bob. To solve this issue with the private key, let's take a look at perfect forward secrecy. Perfect forward secrecy states, if an attacker were to get the private key from the server, they would not be able to decrypt data that was sent from client to server in previous sessions. Because in a perfect forward secrecy scenario, the private key is going to be changing pretty much for every session. So every time a client and server need to exchange keys, they'll be using a different private key. And again, if the attacker were to obtain a certain private key, they will not be able to go back in time and decrypt previous sessions. And when we have a scenario like this, we call these keys ephemeral because they change at every session. Now I have a question. Do you think RSA would be able to use ephemeral keys? It could even be possible, but the problem here is that to generate RSA keys, that takes a while. And so if you want your TLS handshake to take a couple of milliseconds to happen, that wouldn't be really feasible. Now with Diffie-Hellman on the other hand, it's very easy and cheap to generate private keys. So that's why every time we say that we're using Diffie-Hellman for a TLS connection, we're generally referring to ephemeral Diffie-Hellman. And if you take a look at some cipher suites, you're going to see the abbreviation ETH or DHE. And the difference between the static Diffie-Hellman, which is a Diffie-Hellman with non-ephemeral keys, and the ephemeral Diffie-Hellman, is that the private key for Alice and for Bob is going to keep changing. And if the private key is going to keep changing, that means the shared secret is also going to be changing. But the thing here is, it's great that the private key is going to be changing, but it does take some time to generate a private key. So when you compare the RSA with the ephemeral Diffie-Hellman, there's a big difference because RSA, the keys are static, they never change, but with the ephemeral Diffie-Hellman, the private key needs to be generated all the time. If a server wants to use perfect forward secrecy, they usually turn to elliptic-curve ephemeral Diffie-Hellman. And essentially, what this version of Diffie-Hellman does is to use elliptic curves to calculate the shared secret. Now, I'm not going to get into the mathematics behind elliptic curves because that's a very, very complex subject. And that's not something that I know it myself because I'm not a mathematician. But the important thing here to understand is that if you use elliptic curves, the computation of the shared secret, that happens much faster. Just to give you an idea, there is a blog post by Vincent Bernard that it was published many years ago that shows a comparison among RSA, Diffie-Hellman ephemeral, and elliptic curve Diffie-Hellman ephemeral. And for now, just ignore the last bit of information that has the ECDHE-64. Let's take a look at the first three. So we can see here that the difference between RSA and Diffie-Hellman ephemeral is huge. But on the other hand, when you compare Diffie-Hellman ephemeral with the elliptic curve version is much faster. I hope that gave you a very quick intro to the subject. And in the next video, part 2, I'm going to show you how you can configure your web servers to use elliptic curve ephemeral Diffie-Hellman.